To introduce quickly Dan Teal, PNG. We got into the stone strong business about 5 years ago, and since that time we've sold about 10,000 square feet of design build retaining wall systems. Our interest in having Dan here today is to promote all the significant advantages a unit like Stone Strong has to offer. Dan's got a very, very long list of credentials. I've distributed them to the room. Instead of going through all of them, hopefully you guys will find time on your way out to pick up some literature at the back of the room. I will just highlight or hit on a few items here on Dan. He's a graduate of the University of Nebraska Bachelor of Science in Civil Engineering and a Master's of Science in Civil Engineering. He is licensed and or registered to practice in 27 states, a member of 5 professional societies. He's a principal and senior engineer for Teal Geotech, and has a broad background in geotechnical, material, environmental, and structural engineering with over 26 years' experience. Mr. Teal also assisted in the development of Stone Strong Systems, a large-scale precast modular block that you're going to hear more about today. And he developed the design methodologies and software, prepared construction details, and authored most of the engineering manuals for this system. He has designed hundreds of Stone Strong retaining walls located throughout the U.S. Also joining us today from Stone Strong is John Gran, president of Stone Strong, and Drew Black, the Canadian sales rep. So let's get started, Dan.
He's just for a minute.
I'll jump in here real quick. I'm John Gran with Stone Strong. And we introduced Drew Black. Drew has just joined us. He is our Canadian rep for Stone Strong throughout the entire country. And then, of course, Dan is here. Just a couple things that I wanted to share with you. Stone Strong's been around about 10 years. Shaw's been with us about 5 years now. They produce it. They have all the forms. There's some new concepts, some new pieces, some new parts you're going to see today that I have learned that even we're laying on Ryland today. So it's a little bit different thing. If you take your ideas on retaining walls and you're not real familiar with Stone Strong, it's a totally different concept. It's a real big piece, and we actually have some bigger pieces now as well. So I'd like to thank Ryland and Shaw for inviting us up here. This is a great event. It's a nice thing to come up to. And with that, we'll get Dan started and go through the presentation. Thanks.
Okay, thank you. As John said, this is a big piece of concrete. It's a big retaining wall block, and the dimensions are shown here, 0.9 meter tall, 3 feet. 8 feet wide, 2.4 meters. The face to tail dimension is 44 inches or 1.1 meters. It's a big hunk of concrete, so you don't want to think of this like the same as the typical landscape products, 1 square foot products. You're going to want to set all that thinking aside and think about something completely different here today. This is our roadmap, what we're going to talk about today. John's already talked a little bit about the Stone Strong story and how we got here and the relationships. So we'll talk about the concept, the various components that make up the system, the entire system, the design theory and methodologies, some of the construction details, and then some innovative solutions that we've done. Gravity retaining walls. Let's make sure we're on the same page. The niche for Stone Strong is gravity retaining walls. What I mean is a wall that relies on its own weight and mass for stability, is not relying on geogrids or tiebacks or any type of external reinforcement. Just the mass of the blocks, and filled with aggregate in this case, themselves to provide the stability. The beauty of that is we don't have to worry about what comes along later and disturbs our straps or our geogrids, whatever we might have for external reinforcement. It also allows us to do some things that we can't do with some of the other applications available. If we have right-of-way issues or utilities or things that are in the way and I need to minimize the amount of excavation, I don't need to excavate as far for geogrids or for other tiebacks. Another important advantage of these massive elements is the inherent stability. You wouldn't run a piece of equipment like this up behind a traditional segmental retaining wall. They're too subject to, prone to displacement under these severe point loadings. With the mass that we're talking about, the scale that we're talking about, we don't have those problems. The visual scale of the chiseled granite face also is is an important factor in the Stone Strong system. It gives you a lot more appropriate scale aesthetically than the small repeating 1 square foot elements. So we've got this big piece of concrete, this big retaining wall block, but we don't want a one-dimensional system. We don't want just that it'll solve this problem but nothing else. We needed a versatile system. So there's a whole series of companion products go with this that provide that versatility to do things like pond borders and curves and radiuses and corners. We need to be able to do different applications. Maybe we can't solve every problem, but this is not a one-dimensional product. This is a dual-face block used as a barrier on a secondary roadway. We need to be able to plant fences and these things and those sorts of applications. The other premise around the versatility is productivity. This is a productivity story both in the manufacture of the product, which is not so important to you, it's obviously important to Shaw, but also in the installation. There's a cost advantage because of the productivity and how quickly you can install these units. This is an engineered system. There are some other precast modular retaining wall products out there. Mostly they're blobs of concrete. I mean, I don't mean that to sound so derogatory, but they're solid pieces of concrete. This is a structural shape that's intended to reduce the amount of concrete that goes into it, and obviously the cost associated with that, but the transportation cost as well. That shape does a lot of other things for us too. The voids provide a place where we can add drainage aggregate. We've got close to 1 meter square voids in this block that we're going to fill with drainage aggregate. So we've got a lot of drainage capability internal to the blocks themselves. Those voids add versatility in a lot of other ways that we'll show you as we get into some of the innovative solutions at the end of this. The lifting loops are set at the center of gravity, so when we hoist this thing up, chain it up, and lift it up with a backhoe, it lifts level. Small point, fairly subtle, but it's a big deal in terms of the productivity of setting these blocks and installing them, and the size of the crew that's needed to do that. There's a corresponding recess in the bottom. I'll show you a better view of that in one of the later slides. That recess then sits over those lifting loops and provides an alignment mechanism that batters the block. Typically, we're going to batter these at about 100 millimeters per course, although we can do different batters, and we'll talk about that as well. And this is a precast product. There's a lot of reasons we think that precast is an advantage. This is a wet cast, very dense concrete, 28 MPa concrete, 4,000 PSI concrete minimum. Now, in practical terms, they want to get this block out of the form and cast another block in that form as soon as possible. They may be pulling this block out of the form as early as 7 hours, 4 hours, 5 hours. They want to get this thing out of the form so they can make another block, and they need 2,500 PSI to do that. So typically we're seeing 5,000, 6,000, 40 MPa concrete, very high strength. Air and trained for freeze-thaw resistance. Again, this is a wet cast product. It's not like the dry cast blocks. I mean, they have their place, but the dry cast products are very porous. They take on water. Very easy for salt to get in, road salts and things. These blocks are much more weather resistant and chemical resistant in roadway applications. Efflorescence is another problem that the wet cast products greatly minimize. The other thing with precast is we can put anything in that mix you need to. A popular question today was marine applications, saltwater applications. Yes, that's not a problem. Now, the inventory blocks are regular concrete, but we can put admixtures in. We can use sulfate-resistant concretes and things like that, high early strength, to provide salt resistance and chemical resistance for saltwater applications. A lot of the precasters we work with are very creative people. The general philosophy is if you can dream it, they can make it. So we like the precast aspect of this product. The basic block is a 24 square foot block. I work in feet and inches and pounds every day in my life, so you hear a lot of feet and inches and pounds. I'll try and give you the metric equivalents as I go along. But it's called a 24 square foot block because it's 3 feet tall, 8 feet wide. 2.4 meters, or this is a 2.2 square meters of face on every block. This is a patented block, by the way. 2,700 kilograms to the block itself. When we fill that with aggregate, we're talking about 4,500 kilograms or so. You'll note here the recess in the bottom of the block and the lifting loop in the top. That's designed to give us our 100 millimeter setback every course. You'll note in the face there's a faux course. Okay, it appears to be two blocks that are 450 millimeters high, and there is 50 millimeters of setback within that face. So there's some batter within that face. So as opposed to 100 millimeters every 3 feet, we're getting 50 millimeters every 18 inches. We typically do not use a cap with this system, although there is a cap block available and we can put a cap on the wall. We typically use this top block. We just add an insert into the form and recess or cope out the top of the block. This allows us to backfill right up to the face shell, so we have the appearance of just having a 300 millimeter thick wall. I mean, that's all it looks like. So we can backfill right up to it, landscape right up to it. With the voids, we can add fence posts and things right in the voids and right up to the face of the wall. Now, not everything works with that large block. There's a lot of cases where we do need a smaller block. In some cases, we might build a wall entirely out of this block. This is a 6 square foot block, obviously 1/4 the size of the larger block, so all the dimensions are halved. 1.2 meters wide, 0.46 meter tall. The face to tail dimension is the same, 1.1 meter or 44 inches. We can turn tighter radiuses and things like that. We'll use this block to make our elevation transitions. Rather than making steps at 3 feet at a time, we can make our steps 18 inches at a time. That block weighs 1,800 pounds. What is that, about 850 kilograms? There's a whole series of other accessory products, dual face blocks, corner blocks, end blocks. These end blocks are used to provide a finished face on the end of every step. Just adds to the aesthetics of it, provides a much more finished product. We won't get into these, but there are a whole series of accessories available to make this a versatile system that will be able to meet a lot of different applications. As soon as we had this product on the ground, and this goes back, I started engineering with Stone Strong in 2002, 2003. As soon as we had this thing on the ground, we're trying to push the limits, and we needed something bigger. We needed to be able to go taller and taller and taller. So we developed, the first thing we did, we started adding concrete in the field, and we still do this frequently. We'll do cast-in-place tail extensions, basically make the block bigger by adding some cast-in-place concrete in the field. But we are precasters. We wanted a precast solution, so we developed this mass extender block. We've just extended this block now by 300 millimeters, and that is a solid mass of concrete. It adds significantly to the weight. We've got a 4,500 kilogram block. It's now 1.4 meters from face to tail. And by putting one or so of those at the bottom of the wall, maybe two, we can extend the gravity height, how tall we can build a gravity wall by something on the order of a meter, more or less. Just adds to our versatility. Well, if that was good, we thought we'd try and do that better. How can we build that block more efficiently? So this is a brand new product this year. This is a 24-62 block. This is 62 inches from face to tail, or 1.57 meters. We've basically, rather than just adding a big old blob of concrete at the back, we've extended the webs, made the webs longer, and extended the block. That functions similarly to the mass extender block. It will extend our gravity height by about a meter or so. But a lot less concrete goes into that, just under 3,000 kilograms. Okay. Well, if 62 is good, 86 would be even better. So the companion to that is a 24-86 block. This is now 86 inches face to tail, or 2.18 meters. Gives us typically another meter or so in height, certainly another course in almost every case, course and a half in some cases. Again, we've just extended the webs. We haven't put a big mass on the back, 3,300, 3,400 kilograms weight, empty. And then we're going to fill those voids with aggregate. This is a 3-point pick, 3 or 4-point pick. No, these do not, I don't know who asked that, but the lifting loops are in the same location for alignment purposes, so these will not lift level. We'll have to do a 3 or 4-point pick. But typically, we're going to build the bulk of our wall using the smaller blocks. Unfortunately, we lose that picking level capability with these blocks. We're going to move into the engineering that's behind Stone Strong, and as we said, this is an engineered product, and when John and his team started developing this product, one of the first things they did was hire structural and geotechnical engineers. The engineers were involved in this product from the beginning. We had input on the dimensions, outside dimensions of the block, the dimensions of the web and the flanges, and everything in this thing was engineered for efficiency. The thickness of the webs, for example, are based on the minimum dimension for an unreinforced section. So the 24 square foot blocks are unreinforced. The 2462s and the 2486s, those blocks are reinforced. But there was engineering went into this from the beginning, and that's really our emphasis today, is that there's a sound engineering basis for everything that we've done. We have a detailed engineering manual. It's available. You'll find that at www.stonestrong.com. I've always liked having that binder on my shelf. It's always provided me comfort when I'm designing with a product. I can go get that binder and refer to it. And I've kind of changed my ways. Information changes so quickly. We're continually developing new products, updating methodologies, adding capabilities. This is not a static. The engineering manual is not a static product. We update this thing probably monthly. There's some kind of an update made to this thing. So your best bet is to go to the website, www.stonestrong.com. Over here on the right side of the home page is the engineering manual and various other things that you may want to download that we'll talk about. But that is where it's available. The engineering methodologies are compliant with AASHTO, American Association of State and Highway Transportation Officials, and U.S. Federal Highway. HITECH is a third-party evaluation group, Highway Innovative Technology Evaluation Committee. It's part of the Civil Engineering Research Foundation. They're an independent third-party reviewer. They did, at our request, did a detailed technical review of the system. This was 5 years of our lives spent working with these people, getting them information. It's did I say rigorous? About 3 times. It was truly an intensive process. They have reviewed the product. That was a copy of the cover of their report. And they issued a report that the Ministry of Transportation, in this case, can rely on as evidence that the methodology is in conformance, our design methodologies conform with industry standards, AASHTO specifically, but with accepted engineering practices. The other conclusion was that Stone Strong is a viable alternative to traditional retaining systems, including cast-in-place walls. Their position was that this is every bit as long-lasting as your traditional cast-in-place walls. Segmental walls aside, they consider this to be a 75-year life system. Now, I don't know how you ever defend that because we haven't been around for 75 years, but that's their position. So to get to the design theory a little bit, and I won't get into it in great detail, but the primary references that we relied on in developing a methodology that you can apply is the AASHTO Bridge Specification Manual, and there's another companion document published by Federal Highway on mechanically stabilized earth walls and reinforced slopes, and those provide the standards. Those provide government standards that we follow as far as, what safety factors do we need, how do you do analysis, how do you look at different conditions of the wall. And the high-tech report concluded that we were, in fact, in conformance with those standards. The design methodology is based around Coulomb's earth pressure theory. Coulomb's theory for lateral earth pressures is particularly appropriate for this type of system in that there's two factors that they consider: delta, which is friction between the backfill and the wall itself, and we've got these different sizes of modules. That's a big thing. You get a great deal of friction between, and by different size modules, I'm talking about the 2486, 2462, the regular 24s. So that delta is a significant factor because there is a lot of friction between the wall system and the backfill. And then omega is the batter of the wall. The batter of the wall adds a significant amount of stability. So the Coulomb methodology works very well for this type of system. It's particularly well suited, and that's what AASHTO recommends for this type of system. So based on the methodology, and there's a detailed methodology on the website in the engineering manual section, detailed methodology on how to do the calculations manually if you're interested. It's all there. But we run through those calculations with what we did here is we took 4 generic soils, a clay with a friction angle of 26 degrees up to a crushed stone with a friction angle of 38 degrees, 4 different soils, and then 4 different boundary conditions. And when I talk about boundary conditions, I'm primarily referring to what goes on above the wall. Is it flat? Is it sloped? Is there a surcharge? Seismic loading as well we considered as a boundary condition. So 4 different conditions. And we found that the basic blocks, just the 24 square foot blocks, depending on soil conditions, would stand up to 4 meters tall, just stacking the blocks and filling them with aggregate. No geogrids, no tiebacks, no nothing. Now, I will point out this is based on private codes. This is safety factor of 1.5 for overturning. Most transportation projects will mandate the overturning safety factor is 2.0. Okay, but for these sets of conditions, 4.1 meters is a gravity height with stone backfill, level backfill, and no surcharge in a gravity configuration. If we add what we've got here is the mass extender block and then a 600 millimeter cast in place tail extension. Here we're adding a 2462 block, or here a 2486 and a 2462 block, and calculating them out. And in this case, up to 6.9 meters tall. Stack the blocks up. Now that's the bigger blocks at the bottom. 6.9 meters in a gravity configuration. Obviously not as tall with different soil conditions and with different loadings, but you get the idea. These are some pretty impressive numbers. Not every project is going to go 6 meters tall in a gravity configuration. Don't get the wrong impression. Load and resistance factor design is becoming much more popular. The U.S. DOTs are adopting it. They were supposed to adopt it last year. About half of them actually have. I don't know if the Ministry of Transports here have adopted LRFD design. LRFD is just a different way of looking at the loads rather than a safety factor. We're going to factor up, do probabilistic factoring on the loading, factor it up, and a probabilistic factoring of the resistance, factor it down, and then after all the factoring, make sure that the resistance is greater than the loading. It's just a different way of totaling everything up at the end. We've run through the LRFD calculations. These are the same things, same 4 generic soils, same boundary conditions. Gravity heights of up to 3.2 meters with the basic blocks, up to 5 meters using the 2486 and the 2462 blocks. Pretty impressive numbers. Now there's no, when we started designing with StoneStrong, we couldn't find any commercially available software that would allow us to specify stepped modules. Stepped modules is an AASHTO term. Different sizes of blocks. There's some software out there, but you could only use one size block from bottom to the top of the wall. We didn't want to do that. So we wrote our own. This is actually an Excel spreadsheet. Version 3.8 is out on the streets now. This is a very powerful application. It's easy to use, very user-friendly, but a very powerful application will allow you to look at a lot of different load cases. We can do tiered walls, We'll look at some of the details of this in just a moment. We enter a stack of blocks here, enter the blocks just the way we're going to stack them up. The spreadsheet will go to a separate detail library, which I think is the next slide, and get all the properties that it needs for those blocks. You enter your soil conditions, back loading conditions, and all that, and it will determine your safety factors. Or in the case of the LRFD, it'll calculate all the different loading cases that are required for that. There's the detail library. The detail library has all of the basic blocks in it. This is the metric version of it. There are a few. Anything in yellow is something you can edit. You can do vertical configurations with this, a lot of different things. That's where all the data comes from for the spreadsheet. The spreadsheet uses the trial wedge method to calculate the loading on the wall. This is a methodology that's not very commonly used due to the computational effort. There's a lot of calculations go into this. Basically, in the trial wedge method, this is basically a Coulomb earth pressure wedge. Okay, and the Coulomb method, you saw that complicated equation. Really, all that is a vector addition problem. We've got a normal force across a failure wedge. We've got a force against the back of the wall against this wedge of soil that moves. If the wall shifts, that wedge of soil moves downward. Okay. All we're doing in the trial wedge method when we have a non-uniform boundary condition is it goes through and investigates a whole bunch of trial wedges, and then it iterates and solves for the most critical wedge. Okay, it's really just a variation of the Coulomb technique. It's still consistent with the AASHTO standard. In fact, the new California AASHTO standard requires, or not, the new California LRFD standard requires that you use the trial wedge method to resolve the back slope conditions. Okay, so the spreadsheet is based on that. That all happens transparent. You won't see it, but it does report all the results to you. There are cases where we will want to build a grid reinforced wall. So our niche with this product is gravity retaining walls, but every now and again we're going to run into a case where we need to go taller and we can use grids. That's okay. We have done interaction testing with the Stone Strong blocks, and here's Centene geogrids. We have done testing with some other geogrids. All that data is available. Those test reports are available. They provide the engineering properties that you need to design grid reinforced structures using Stone Strong. From there, we'll move into the construction details. There are about 80 construction details, something over 80 construction details or typical details in the detail library that are on the website. They're on the website both in PDF and DWG form. So there's PDFs. You can very quickly browse through the library, see what you're looking for, and then you can download zip files that have the actual AutoCAD DWG files. Our intention is that you take the standard details or typical details and you customize them to your specific application. There's no possible way you can address everything in a detail library. We do expect that you will customize these things. So there's what they look like. This is not a standard detail. This is actually the last of the innovative solutions that we'll look at in a little bit. But that's what we expect you to do, is take those details and work with them and do the engineering for your specific project. We're going to use some of the details to talk about some of the characteristics of the block. I told you that we needed a versatile product. First thing we looked at is radiuses. The back flange of the block is 75 millimeters narrower than the face shell. So we've shaved 75 millimeters off both sides. So when we set these things in a straight line, we have between the tails, we have 150 millimeters. Okay? If I turn a convex radius, an outside curve, and when I turn those tails together and they touch, that is my minimum radius. So we've done that for you, and we find that, I'll give it to you in metric, 15.7 meters is your minimum radius, okay, when the tails touch, 15.7. If I turn a concave radius, I don't have a problem. The tails are not going to touch, but my problem is that when I set these in running bond, the next course up is going to want to cut the corner and overhang. Okay, so we've done a similar evaluation and found a 14.1 meter minimum radius in a concave configuration. Now, as a designer, I don't want to saddle my contractor designed to absolute minimum, and he can't make any mistake. There's no margin for error. So I would suggest that typically somewhere in the 18 meter or so range would be an appropriate minimum radius for the 24 square foot block, okay? About 18 meters. You can go a little bit less. I would note also, especially in this case, this 15.7 meter minimum radius, that occurs at the top course. If you're laying out at the bottom course, you need to account for that 100 millimeters of setback in every course. So you can use this table and just look up what your radius needs to be. Okay? 18 meters works pretty good in most highway applications. Now, if I'm doing a parking lot on a private project, suddenly 18 meters doesn't look very practical, but that's okay. I've got other options. The 6 square foot block, as I said, is an accessory. We can very easily transition from 24s to 6s and then back to 24s if we need to. We went through the same analysis with the 6 square foot blocks until the tails touch. 4.9 meters in a convex configuration at the top course, 4.1 meters in a concave configuration. So somewhere around 5.5, 6 meters is an appropriate minimum radius for the 6 square foot blocks. That starts to work in tighter quarters like a parking lot, that type of thing. We have corner blocks. We can do 90-degree corners, 45-degree corners. So if you have something tighter than that, you probably just want to use a corner anyway. I showed you the end block earlier. We use the end block to provide a finished end when we make a step in the top of the wall. We use the 6 square foot blocks, and there's this 3 square foot block stuck in there just to keep everything on running bond. Same thing at the bottom of the wall. We can make our steps in these shorter increments, 460 millimeters. We typically will set these on a granular base. We can set them on a concrete base. We've got the spreadsheet will address all of those calculations to address sliding across a concrete base. But typically, we're going to set these on an aggregate base, crushed aggregate. We want a well-graded material typically, maybe 250 millimeters thick, 1.5 meters wide. If we're using some of the larger blocks, we do need to make that base wider. Just simply compacted aggregate base. And we do not typically embed these at frost depth. If I can get back, come on. You won't go back for me. I'll get you there. Okay, we typically do not embed these at frost depth. Typically, we're only going to embed these maybe 250 millimeters or so. We've done a lot of work in cold, in freezing climates. We do a lot of work in Maine, Massachusetts. We actually have done a lot less work in areas like Texas where it doesn't freeze. But these are not very frost susceptible. It is a flexible system if it moves modestly, but with the weight of the wall, these do not move around very much. So typically, we do not embed them at frost depth. Now, I'm a geotechnical engineer by education and practice primarily, so you don't get to hear me talk for 45 minutes without a little dissertation on backfill compaction, how important it is. Compaction of the backfill is critically important to stability of the retaining wall. Okay? We're relying on the properties of that backfill in the design and the stability of the wall. If we do not compact the backfill, we won't have the properties that we've designed for. We won't have the shear strength, okay? Fairly straightforward. Now, many products will allow for or even mandate a reduced compaction immediately behind the face. The small blocks typically do, some of the panel products do, and they'll say, 90% of standard Proctor compaction for 3 feet behind the face. The problem is that these elements are subject to disturbance when you're compacting, okay? That's not the case here. This is 4,500 kilograms. Once we fill it with aggregate, it's very stable. We can run our compaction equipment and whatever equipment we have right up to the back of the block and compact right to the back of the block. I want you to do that. We need to compact that backfill so that it has the properties that we're counting on to support the wall. In my practice, we have evaluated wall failures that were primarily attributable to that poorly compacted zone behind the face. It's a bad idea. I don't know how you defend that on an engineering basis. Compact your backfill. It's very important. Okay, we'll move from there to some innovative solutions that kind of show some of the versatility of the product. This is a project near my office, about half a mile from my office, in the city of Omaha. City of Omaha has a mandate. They do not allow geogrids on their projects. They've had too many problems with people cutting them after the fact, so they don't allow geogrids. This project was designed and bid and let, using cast-in-place concrete walls for the entire job. What they didn't take into consideration was some new utilities that had been installed. This was actually on the shelf for several years before it was actually built, and there were some new utilities installed that weren't on the plans. They had a bunch of utilities that were in the way, were going to have to be relocated. They didn't have time. They didn't have the budget. The contractor walked in my door and said, "Fix it for me. What can you do?" And we did fix it. We completely redesigned the job, a value engineering proposal using Stone Strong, all gravity retaining walls. We were able to avoid all the existing utilities. He was able to build this project in less time than he had budgeted for the cast-in-place walls. Didn't save the city any money. Somebody made off like a bandit, I think. But it was a successful project. One of the things that went on, there's a cemetery back here, a very little room, and they had the traffic signals originally set on a drilled pier, and then that pier came up as a pilaster through the cast-in-place wall, according to the original design. Well, that wasn't too hard. We just made sure we laid out our blocks so that the blocks came together over that pier, left the rebar sticking out of the pier, brought the blocks together over that bar, the last one threaded over it, filled the voids with concrete, and did the same pilaster extending through the wall, extend the pier through the wall to support the traffic signals. So it was a successful project. That's not rocket science, but the point is, with the voids and the versatility of the product, there's a lot of things that you can do. This bridge is in New York State in the Hudson Valley, middle Hudson Valley. The counties up there, a couple of different counties have adopted this, and they're building these bridge abutments using county crews. They've built about 14 of them, to my knowledge, maybe more now. This is a structural abutment. This abutment is carrying the bridge. There's no piling behind this, anything like that. This is a shallow foundation. In this case, it's on a granite ledge, but they've got some of them that are on just gravel, shallow foundations on gravel. And then they put rebar in the block voids and fill the block voids with concrete. So this is a structural abutment that is supporting the bridge on the blocks or on the concrete through the voids. It's just a natural. Then the wing walls are just conventional retaining walls. You could do this on a pile or pier foundation, kind of the same way. Extend your rebar through the voids and fill the voids with concrete. Pipe penetrations, a lot of different ways to do this. We can do a cast-in-place head wall after the blocks are set around the pipes, or in this case, we cored through the blocks. Now, we knew we were going to do this, so we've got rebar in the face and tail, and then set this up on the coring jig at the precaster and cored some holes. Now, there's two pipes here, and you might wonder why. This one's got water coming through it, obviously a drainage pipe. This is a critter crossing. It was shown in the civil drawings as a critter crossing. And there was some dispute between the town engineer and the contractor whether he needed to crawl through there and put peat moss all the way along this critter crossing. They stood there and argued about it, and they were interrupted by a couple of chipmunks who were using it. So they settled on no, they didn't have to crawl through that. Here's my last innovative solution. This is what I would call a hybrid application. This, again, is in eastern Nebraska in the central U.S. The town engineer here said, that's a big wall. You can put geogrids in that. That'll be fine. But I've got to put in a water line, a sewer line. I've got to bring communication cables, power. I've got to bring all my utilities across this. This is a land bridge, basically. I've got to bring everything across here. No geogrids in the top 2.7 meters, 9 feet of my wall. No geogrids up there. Oh, and I need a barrier. I need a parapet up there. Well, okay, that's That's a challenge, but turned out to be quite doable. We started with a 6 square foot block at the bottom of the wall so I could get a geogrid right near the bottom of the wall, and then 24 square foot blocks with geogrids, another 6 square foot block at the top of my reinforced zone. This was very important because I've got a concentration of grid tension right below the gravity section of the wall, so I was able to get 2 geogrids stacked on either side of that 6 square foot block. My next problem was I've got clay soil here. My gravity wall didn't work on the top, so I had to use a mass extender block to make my gravity section of the retaining wall work. And then I've got dual face blocks stacked up with a cap in this case as a parapet. We came in here and stained this as a 2-color stain. Typically we'll stain these blocks in place, use an acid etching stain and stain them in place after installation. They came in with a brown with a sprayer and sprayed it all with this brown stain. They came in with a dark brown stain and just sprayed some highlights on some of the high points on the block. If you stand 10 feet from this wall, you'll think it's sandstone. It looks really good. So there's a lot of creative things you can do with stain. We've seen some 3- and 4-color stains even that are sponged on that look quite impressive. A lot of different things you can do with this system. The system has built-in versatility, but it is an engineered solution. It's a sound engineering solution, and with some sound engineering to apply it to a project, you should have a long-lasting solution that you can be proud of. So, with that, I would be happy to take any questions. Must be getting late. Can you please? Yeah, these were just launched, so they don't have the forms in the plant yet. But if you need them, he'll get them. He'll get those forms in here. No, I'd prefer it's free draining, but if all you have is cohesive material, I'll take cohesive material. Behind the blocks. Now, in the cells, I want drainage aggregate. Okay, I want a screened, coarse aggregate in the block cells. And we're not only relying on drainage, there's a lot of things going on in those voids. In the interaction testing, one of the things you do in interaction testing is just put 2 blocks on top of each other, put a normal force on it, and shear one block off the other. Okay? Well, we looked at that rebar or the steel alignment loop and said, we're not going to fail that. So we got the torch out and we cut it off before we did our testing. And did the shear just relying on the aggregate through those voids. Those voids line up, the aggregate interlock through those voids to provide shear. And we found that we've got plenty of shear, and those internal stability numbers are built into the spreadsheet, by the way, so you can do that internal analysis. So in the voids, coarse drainage aggregate. Behind, we can use probably what's on site. The height tables you saw, I'd listed a clay material, and then also sand, and then a gravel, and then a crushed aggregate. So we can design for whatever properties of material you have on your site. Obviously, the better the material is, the taller the wall will stand in a gravity configuration. So, all right. Thank you all.
All right, that concludes our sessions for this afternoon. So everyone, hope you all learned a little something and going to walk away with some knowledge. I know I certainly have, and I think it was been very, very, very beneficial from a supplier's point, and hopefully you guys feel the same way. So thank you all for attending, and